go. Okay. Can you see okay? Is that okay? Yeah. We'll get this lesson done this morning. It's quite short. It's very nice, a very useful theorem, Lami's three-force theorem. Now, this is a special system in physics. It's special because there are three forces acting on it and the system is in equilibrium. So, there was an example I didn't do last week from the cantilever lesson, which I'm going to do now because it's relevant to this. It's the example of the ladder against the wall. So what I'll do, I'll make one up. Now the wall is smooth and the ground is rough. And here's the ladder. So we'll have a force here. I'll call this S. There's a force here, which is R. There's a force here, which is W. We'll keep all the distances nice and easy. We'll say this is, we'll go with the classic 3 meters, 4 meters. No. We'll make it even easier because we'll go with 6 meters, 8 meters, and 10 meters for the three sides. There's one force that's missing here. Can anyone see what it is? One force that I didn't draw. Can anyone see where it might be?
Isn't it the opposite of S?
No.
Is it
From yes, yeah. Yeah.
Oh, yeah.
If you think about it, the ladder wants to fall this way, doesn't it? And it wants to fall this way. Now, this is smooth, so to stop it falling, there must be some friction force here to the left. Yeah? On the ground, because the ground is rough. Yeah, is that okay? Yeah. Now, let's see what equations we can make. Alright, so we can say S equals F, yeah, that's equation 1. What else can we say? We can say R equals W, which equals mg, whatever m is. Let's make this also easy, 10 kilograms. Okay, so we get R equals 10 times g, that's 98.1. Okay, that's our second equation, and that's nice because we have the R. Well, we don't know S and F though. And the third equation, we can use the turning force. What would be a good turning point to use? Yeah, I think so. Now, can you tell me why you picked that one?
Because there's two forces.
Yeah. So this one clockwise or anti? Anti? Clockwise. Now there's a problem. Remember the formula is force times distance. Yeah? So you have a choice here. You can do this distance, but then here you have to resolve, right? Because you only need the perpendicular. Yeah? Or, what is also nice, you could just do this force, but times this distance, because that's the perpendicular distance. Yeah. So that one would be 3W equals, and then this one here, and this distance, what would that be? 8S, right? Yeah?
How do you know it's 3 W's?
Oh, because it's in the middle.
Yeah, but how do you know it's 3?
It's a geometric thing. It has to be in the middle. Now,
W's in the middle.
because W is in the middle of the hypotenuse. So, it seems like it's wrong. It seems like you can't guarantee it.
Yeah.
But trust me, it's always in the middle.
Okay.
And in fact, I challenge you to try and prove it as a little exercise later. You can it's just a bit of trigonometry. You can prove that it always splits the base in half as well. And
So
it all,
half the hypotenuse is half the base.
yeah.
Well, it makes sense if you half.
Everything scales down by 50%, yeah. So we get S equals 3 over 8W, which is 98.1. Okay?
Why is it 8
This distance here is 8 to the S force. Isn't it? 6, 8. This is 8.
Yeah.
Yeah? Oh, confusion, look.
It's a perpendicular line.
Stephen used confusion. It is super effective. She hurts herself in her confusion.
okay, I get it.
Are you sure? Confusion wore off. Okay. Right. S is 3/8 times that. And
3,679.
what is it?
679.
67.9?
3,679.
3 point?
Yeah.
No. You must put the decimal place in the wrong spot. It must be
Yeah,
36.9 perhaps.
I did. 36,79.
36.79 newtons. Okay? And then lastly we can get the F, because the F is equal to the S. So F is 36.79. So finally, what I was trying to do here, these two forces combine to make a force here, right? And I actually wanted this angle. So theta would equal tan inverse or over F. Or over F. Okay, what's that? Should be pretty steep. Like 70, 80 degrees.
69,44
Degrees.
degrees.
Yeah. Now you don't need to write that down, because what I'm going to show you today is another way to do this, which is a lot quicker, called Lami's three-force theorem. So we'll go. I just want to keep this here. The answer, I want to show you that the other way gives the same answer. Okay. So let's go back to Lami. So Lami is for a situation where you have three forces and it's in equilibrium. Just like here.
What about the frictional force?
Yeah, you can combine them into one. So you could say, here's the ladder.
Oh, the resultant, yeah.
Yeah, you could say, there's the ladder. We have a weight. We have a reaction. And then the two of these can combine together into one force. I'll just call it Q. Okay? Yeah. So, this is Lami's three-force theorem. When three forces act in the same plane on a mass in equilibrium, then all the lines of action meet at one common point. Now, before you write that down, I'll just draw precisely what that means on the left here. So it means if you have some mass, and there are three forces acting on it, there's force 1, there's force 2, and there's force 3, and in total it's in equilibrium, meaning it doesn't turn or it doesn't move, then Lami said these three forces must meet at some shared point. Okay. Also what Lami said, which we'll see in a moment, is if I call this angle theta 1, if I call this angle here theta 3, and I call this angle here theta 2, then Lami also has given us a formula. We won't look at the proof. You can actually have this formula as a relationship between the forces and the angles. So there are two ways to state Lami. You can state it quite simply as all forces meet at one point, and that's useful, which we'll see in a moment. Or you can use this formula, and that's also useful for a different type of problem, which we'll see in a moment. Okay, so these are the two versions of Lami's theorem. Now you can write these down. And if you like, you can draw this picture if you think it'll be helpful in your notes. Oh, I should have brought my jacket.
Can always go and get one at the house. Yeah.
Well, I have my jacket, it's just in the office. We are missing Diego, yes.
He's in Brussels.
Is he really? What the heck is he doing there?
He's getting an MRI.
Helping with the negotiations for Brexit, is he? He's getting what?
He's getting an MRI done.
Why do you have to go to Brussels to do that? Could they not do it here? Is it,
No.
like, does he have a private clinic or some better service?
I think the doctor he was going, the urologist
Is in Brussels?
yeah.
Still.
He had a tumor excised,
Ah.
which was malignant.
So is this a regular checkup?
No.
Oh.
Yeah. It was just excised, like, that's why he started a week after in DRC.
Really?
Yeah.
So something must have happened to force him to go back to Brussels to have this checked out then?
Yeah, well, his blood tests were negative, but it's just a safety
Ah, good, okay.
to, make sure.
Yeah,
it's
gotcha.
not
Yeah.
metastasized.
Okay, well, hopefully it'll go well for him. So,
Yeah.
when do you think he'll be back?
He's coming back on Wednesday night, so
So, I'll see him later on the week then,
yeah.
perhaps, yeah. I wonder, have any of you seen this theorem before? Lami's theorem. You've seen Lami's before?
I feel like this we learned in maths.
Well, it's interesting because the second version is very similar to something in maths called the sine rule.
Yeah,
A over sine A equals B over sine B, yeah. But what about in physics? Yeah.
So why did Lami get his theorem if it was
Yeah.
already a theorem in maths?
I know, this is great for Lami. Like, this is his one achievement in physics, his theorem. Good for Lami.
Who was Lami?
I checked this last year actually. Who was he? Was he a German physicist?
Doesn't really sound German.
Or maybe not. Italian perhaps? Anyways, this is Lami's big accomplishment. Right, have we got that?
Not yet.
Lami's theorem is very helpful in the exam. It's a nice a shortcut. Okay, we ready? Yeah, let's have a look. So I have a couple of, actually have a good few examples, although I really just need to do two examples. So what I'll do, I might do that one. But I'll definitely do the ladder, and I'll definitely do this one. Let's have a look. So what I'm going to do, I'm going to go back to the ladder, and I'm going to show you how to use Lami's theorem on this ladder, okay? So I just need to put in the distances. This distance here, what did we say that was? That was 8 meters, isn't it? And then this distance here was 6 meters, and then this distance here is 10 meters. Okay? So Lami said these three must meet at one common point. So if I go dot, 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 across here, dot, 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 across there, and so this one must meet, no choice about it, must meet right here, where the others meet, okay? So there's a horizontal, there's vertical, must meet there. Now, if you look at this triangle, how big is this height? 8. And this base?
4, 3.
3. 8, 3. This angle is tan inverse 8 over 3. Is this 69.4?
Yeah.
Pretty sweet, huh? Pretty sweet. So let's have a look at another example, okay? If you want to sketch that as an example of Lami, we'll have another one. I'll draw one beside it. So I think I'll do 2 more examples maybe. I like this one with the 10 kilogram, radius 5, and the string is 8. So in this example, you have the wall, you have a ball here, and there's a string from the ball to the wall, and the forces are as follows. There's a force here, obviously. The wall is smooth. That's a reaction. Okay. There's a force here. It's a tension. And then there's a force here, which is a weight. Now, what did I say it was? 10. That's 10g. Okay. The radius of the ball is 5 centimeters. Okay. And the length of the string is 8 centimeters. Right. Let's see what we can do with Lami this time. So can anybody tell me where the 3 forces meet on this picture? Well, this reaction force is horizontal here, isn't it? And this is vertical. So then this one must be going like this through the center as well. Okay? How big is this hypotenuse?
8.
Is it
0.0.
8 plus 5?
Yeah.
Yeah. So that's a 13. How big is this? 5. So how big is this? 12. From Pythagoras. Okay. Now, we'll call this angle theta. Okay. If you were to take this t and resolve it, you'd have t this way and t this way. If that's theta, can you all see that that's theta as well? Yeah? Which, this one up here, is it t cos or sine? Sine. So are we all happy that we can say t sine theta equals 10g? Yes? No? And t cos theta, what will that equal? Or? Yeah? But I want to know t. That's my question this time. What's t? So t is 10g over sine theta, which is 98.1. And we actually know sine theta. What's sine theta if we look at the triangle? What over what? The green triangle. What's sine theta? Yeah? Yeah, or we could just go straight into saying sine theta is 12 over 13. And now we know the t. Yeah? You know that meme, Futurama meme with Fry, where he's looking and he says, can't tell if blank or blank. Like, can't tell if my students are confused or just tired. Which is it?
I think Stephen used confusion.
Yeah,
Super
yeah,
effectively.
yeah. I didn't think this one was that confusing though. No, I don't know.
Just went a bit quick, that's all.
Yeah, but that's, Lami's is so useful because it cuts out a lot of work. It really shortens the problem.
So instead of doing the moments.
Exactly, it cuts that all out. Will we do one more example? Will you see? Actually, I can do 2 more examples because I can do the cantilever we did last week. Yeah, but the next one is something I've seen in the exam a few times. This one here. A 1 kilogram mass hangs from the ceiling with 2 strings of 30 and 40. So here's the ceiling. and you have here 1 kilogram,
One.
and you have 2 strings here, and this one is 30, and this one here is 40. And my question is, what is the tension here, and what is the tension here? That's my question. Yeah? We understand what we're looking for? So let's use Lami. So to get started, I'll just make my life a little bit easier by putting in an X and a Y here. Okay, so if this is 40, how much is this here?
180 minus. No.
It's 50, isn't it? Yeah. For just this piece, yeah, 50. And if that's 30, how much is this? 60. And is that right? 60 and 50.
Shouldn't be 55.
Huh? That's 40.
Oh.
Sorry, isn't it?
Yeah, 90.
Yeah, 40. 40. So that's a 50. Yeah?
No, yes.
And this here? 60. So altogether, 110 for this whole angle. Yeah? Okay, let me just draw in the other force here. How big is this force? This is 9.81, isn't it? 1G. Okay, that's 110. How big is this angle?
90 minus 50.
Yeah, so how big is this?
40.
40. And how big is this? 90. 90 and 40? 130. Okay, and then how big is this? It's 30. And 90 makes altogether 120. So if you were to draw this little picture here, this is exactly what you have. You have 110, 130, 120. T, S, 9.81. Lami said that T over sine 130 equals S over sine 120 equals 9.81 over sine 110. So you can take this guy with this guy and get T equals 9.81 sine 30 over sine 110, right? And then you could take this one with this one, and you can get S equals 9.81 sine 120 over sine 110. So we are finished. So what's the T and what's the S, please?
T is 5,
Yeah.
22.
2 newtons. So S must be about roughly the same.
Calculators.
Yeah.
Cool.
Oh, that seems a bit too big. No, it could be because they're actually quite similar. Yeah, no, okay, yeah, it could be. Yeah, 9.04 newtons then. Yeah.
Well, from a 10-degree angle, it's like almost.
Yeah, I was thinking because they were kind of similar, it should be symmetric, but there's a big difference with only the 10 degrees. Yeah.
This is really useful.
Isn't it?
Yeah.
One more example we'll do. I want to do the one we did last time, the cantilever one, if I can open it back up.
The one you said we must try.
I'm not sure. Where's it gone? No, we did the ladder already. This one here, wasn't it?
How to do that one.
I thought we did this in class, no? Anyways, we're doing it now again with Lami. It's 40 centimeters. That's 40, okay. And it's 10 kilograms, so that means there's a weight here of 10 G. Has a 2 kilogram mass placed at the end.
Oh, yes.
2g. Oh, I don't think this will work actually because there's too much on it. Yeah, because then what you'll have is you'll have the tension here and the reaction here. So if we want to use Lami, we'll have to get rid of one of these forces. So what I'll do is I'll just do this question where we have a 10. No, let's make this one a little bit harder. What we'll do is we'll make the sign not symmetric. So what I mean is maybe the center of gravity is nearer inside. Do you know what I mean? Yeah. So I'll put the 10g here, and we'll try and keep the distances easy. We'll say this distance is, what did I go with? 40? Okay, let's say this one is 10 centimeters and this one is 30 centimeters. Okay, and then 40. So we'll make this side 30 centimeters and we'll put the rope here and we'll make that side 50 centimeters. That works, doesn't it? 30, 40, 50. Yeah? And we have a tension here and we have our reaction here. Okay, let's see Lami's in action again. So, in blue, I'll draw this straight up. Okay, I'll draw this, it must meet here, and there we go. Okay, so if I look at this triangle, what do I know? I know that this side is 10, don't I? Yeah. This is 30. Ooh, so I could know this. Could anyone tell me what this length is? Yeah. Anybody know this length?
It's 30 squared tube.
What do you think?
It's 30 squared tube.
Oh, not that, no. Anybody? Anybody? No? Wait, what did you say? Can I see? Show me the calculator. Maybe I misheard you. No, not that. Sorry. Well, I think it's going to be, if you think about it, this point here is 3/4 the base. So this point here will be also 3/4 the hypotenuse. Just like with the weight. The weight is in the middle, it splits the base in half. Yeah, you know this from maths. You do know this. You know when you have this situation in maths. Perhaps. These lines are parallel. Whatever the ratio is here, it'll be the same ratio here. Yeah? Did you learn this in school? In geometry? So if I go back here, because these are parallel, it means it'll be 3/4 of 50. What's 3/4 of 50? 37.5 centimeters, is it? And so what is this piece here? It'll be 12.5? 12.5 centimeters. Okay, well, look, if that's 37, that's 12.5. Now, do I have enough to get the height? Oh yeah, can somebody use Pythagoras to give me the height here, please?
$22.5.
22.5?
I think so.
Square root 37.5 squared minus 30 squared?
Yeah.
Okay, what is it?
Did you get 22.5?
22.5. Yeah, so look, now you know this and now you know this. Can you know this? Of course you can. It will be tan inverse 22.5 over 10. Okay. Can you know this? Of course you can. You could have known it at the start. It would have been tan inverse 30 over 40. What's that one? Okay, so look at what equations I can make. I can make or cos 66.04, that will equal t cos 36.87. And then or sine 66.04 plus t sine 37.5, what will that equal? Those they're the two up forces, what will they equal? 10g. Yeah? What type of problem is this like in maths class? What lesson is this like in maths class? You could write this as minus equals 0. What does this remind you of in maths class? What lesson? Yeah, what's it called?
Simultaneous equations.
Simultaneous equations, yeah. Now, of course, you'll have to convert these into decimals and go through it, but now it's just a boring maths problem. We've done all the hard work to get to here. Now it's just a regular maths problem. Yeah? I've only seen this one in the exam once. And you don't have to use Lami. You don't have to use Lami. You can do it the other way, of the turning forces. You know? But I think we all agree for at least questions like this one, Lami was a really good idea, wasn't it? And what do we think about this one? Good or not good for Lami? Useful or confusing?
First one was always confusing, but now it looks...
What about with the ladder?
Yeah.
Useful or not useful to use Lami? Useful. But I'm not sure if you're convinced about the last one. I don't think you were too happy with it. Okay. Anyways, I'll leave that there for a second if you want to copy it down. And I think that, yeah, that's the last example. You can have a look now at the homework. It's a little bit messy here, sorry.
So I must email you my...
Yeah, tell me you need access to Maths Part 1 and I'll add you to it. This is a mess. It's a little bit messy, but if I just write in alpha, that one was alpha, and then beta, and this one was beta, so that was beta, and that was alpha then. Drone, is it? No, there's nothing inside.
It is inside.
Where?
Oh, yeah, it is.
Oh, it's a wasp. Oh, would you relax? Relax. Oh, good. Now, would you blame it if it didn't want to go outside?
Oh yeah.
I'll leave it open, it might find its way out.
It went in that little crevice.
Oh, if you slam it shut, you'll squish it.
Where was squish it?
If you close the window, you'll probably squish it.
Where is it?
It's somewhere in the window frame.
No, it went in there.
Oh, in the white thing?
Yeah,
Really?
it went in here.
Oh yeah, I saw it right there.
Ah, good, okay. Well, it's happy to leave it alone in there, so.
Wasp stingers are nasty.
It's really surprising to see a wasp in the middle of October.
Yeah.
This is somebody who has managed to hang on since the season changed.
Yeah.
Oh.
I heard they're quite troublesome here, they're like the top of the worries.
Oh, they're not. They're not work. Like, I mean, there's plenty of times when I've been waiting for like a train or something and I saw a wasp and, you know, you would see it land on your hand. As long as you don't move, it'll leave after a few seconds because it'll discover that you have nothing for it and it'll just go, you know. So what annoys me when I see people starting to do all of this stuff, I'm like, all you're doing is you're making the wasp angry, you know. If you actually didn't move, it'll go away much quicker. Anyways, let me close this here, sorry.
Let's see that.
Yeah, I can see it.
Really?
If you look through there, you can see it.
Don't freak her out.
Do you think he survived the rains by being in here this whole time? Because how would it get inside? That window was open over the weekend, yeah.
It was open over the weekend.
Yeah.
Well, that's how I suppose.